Okay, so this is problem 7.12 out of Griffith's quantum mechanics textbook. And it's a great problem for perturbation theory and degenerate perturbation theory, all that good stuff. And it would be a great problem for a professor to put on an exam. So we're going to go through it, but before I do that, if you wouldn't mind liking my video and subscribing, I'd really appreciate it as I'm trying to build my channel a little bit. Okay. So we have our Hamiltonian, and part A tells us to write down the eigenvalues and the eigenvectors of the unperturbed Hamiltonian, which is when epsilon is 0. So our Hamiltonian is the following. I'm just going to copy it down. Okay. And a lot of times we can think of our Hamiltonian as the sum of our unperturbed Hamiltonian, which is like essentially what this is, plus this factor lambda times h prime. And this isn't an eigenvalue. We use lambda for both, but they're different values. That's actually not h naught. This is h. But we're about ready to find h naught when we let epsilon go to 0. So h naught then is v naught 1 0 0 0 1 0 0 0 2. Okay. Now to find the eigenvalues for h naught, all we need to do is the determinant of h naught minus our eigenvalues lambda times the identity matrix. So I'm just going to kind of write this out one long time. We have v naught 0 0 0 v naught 0 0 0 2 v naught, taking the determinant of all this, minus lambda 0 0 0 lambda 0 0 0 lambda. And we're setting that determinant equal to 0. Okay, so this is v naught minus lambda 0 0 0 v naught minus lambda 0 0 0 and then 2 v naught minus lambda, just combining these two matrices, and that's equal to 0. So finding this determinant is pretty easy. I've done videos on how to find determinants if you're not too sure. So we'll have v naught minus lambda times v naught minus lambda times 2 v naught minus lambda, and we're going to set that equal to 0. And clearly we have two cases where lambda is equal to v naught, and one case where lambda is equal to 2 v naught. Okay, so these are the eigenvalues for h naught. And this is telling us we have our degeneracy because we have repeat eigenvalues. Okay, so now we need to find the eigenvectors or eigenstates. So we'll start with lambda equals v naught. So the way that we solve that is this little matrix here that I just made. We're going to replace lambda with v naught. And what you'll get is zeros everywhere, except in the bottom corner you'll have 1 v naught. And this will be some matrix we'll call xyz. Should be equal to the 0 matrix. So if you multiply this out, you'll get 0 times x plus 0 times y plus 0 times z equals 0. The same thing here. but in the bottom you'll get v naught z equals 0. So from the third equation, it's clear z must be 0. Now, x and y are what we could call free variables. So in one scenario, we could have, I want to use the right marker, 1, 0, 0. We'll call it as the first eigenvector. I should probably use psi because that's what we use. And in another case, we could have 0, 1, 0. Now technically you could have picked a whole bunch of different types of vectors, but these two are normalized, so they have a magnitude of 1. Z has to always be 0 no matter what. X1 and Y1 are sometimes called free variables. And we have our two vectors for our two different eigenvalue. Well, the two times the times that eigenvalue repeated, which is twice. Okay. And then we can do the same thing for our other eigenvalue of 2v naught. Okay. So that would be, you would do the same thing, plug in 2v naught. This time you'll get minus v naught, 0, 0, 0 minus v naught, 0. All zeros, let's call it x, y, z again. Again, equal to the 0 vector. And if you do that, what you'll see is x must be 0, and y must be 0, and z is what we would call free. And if it's free, we'll pick 1. That's the easiest, and lets our magnitude be 1. So we have 0, 0, 1 as our eigenvector. Okay, so that was part A. Part B says solve for the exact eigenvalues of h and expand each of them as a power series in epsilon up to the second order. Okay, so with B, again, our Hamiltonian is h naught plus h prime, or h prime equals lambda minus h naught. And if you go up here, you're essentially letting lambda equal 1, which is what we end up doing after we're done proving that that's true. Okay? So then, h prime is the perturbated, or the original h that we had above, minus our unperturbated, which we have over here. So we have to do h minus h naught to get h prime. So our h prime vector is going to be minus epsilon 0, 0, v naught, 0, 0, epsilon, 0, epsilon, 0. Okay, if we just do this little matrix arithmetic. And what we want to do, I'm just going to rewrite our eigenvalues, so what we found up here, and I'm just going to rename them into variables that the book uses. So our first eigenvalue was v naught, and that corresponds to a wave function, or eigenstate, of 1, 0, 0. The second one equals v naught as well, and we got the different state over here, 0, 1, 0. And once again with the third one, that was 2v naught. So I'm just moving this information down here and rewriting it in variables that is in agreement with the book. So to find our energy corrections, this is telling us the order of our correction. So this is the first order. It is essentially the matrix element. So psi, this is whichever wave function we're interested in, whatever eigenstate, unperturbated, times our perturbated Hamiltonian, and then our wave function again. Okay? So if we look at the first case, let's just say E sub 1, first order correction. Again, that's what that means. We want our unchanged wave function, our matrix H prime, and again our wave function. Usually they kind of put parentheses around this. And remember, this turns our matrix on its side. Comes 1, 0, 0. This is right above, so I'm just going to write it down again. That is the Hamiltonian that we found. And this is right side up. And of course there's a V naught because our matrix includes a V naught. Okay? So this is just matrix multiplication. Hopefully you're okay with that. And this will be minus epsilon 0, 0. So minus epsilon V naught when we multiply these out. As for the second one, same process. First order correction. And take our other wave function, and we're going to find our matrix element. So this would be V naught 0, 1, 0. All of this stuff that we found. Zero, 1, 0. And if you multiply that out, hopefully you see this will be 0. This is just matrix multiplication. So that's all that is. And then for the last one, same exact process. It's a little rinse and repeat, but that's how you get better at it. You keep practicing. So remember what our vectors are. That's why I wrote them all down again, because it kind of took a second to find them. And then 0, 0, 1, V naught. Once again, if you work that out, it's 0. So that is our first order correction, but it says up to second order. So that was our first order correction. I should make a note of that. That's what these are telling us. It's the first order. The second order, slightly different equation to use. Again, this is all in Griffiths, but it tells us the second order correction for the nth state. I don't know why my iPad just freaked out like that. Summation for k not equal to 0 of psi sub k h prime psi sub n. This is all squared, and we're actually going to divide this by our 0th order correction energies. Okay, so just to make some sense out of this, let's just talk about what all this is. Psi sub k 0 is the unperturbed or unperturbed, different, we'll call it different, eigenstate. By different, I mean the eigenstate that's not associated with the energy that you're looking to create, or not create, but look into. H prime, again, we've been working with that perturbated Hamiltonian. Okay, and then E sub n there, that's our unperturbed energy eigenvalues. Energy eigenvalues of psi sub n. And same thing with k. E sub k, I mean. And those are your other states, besides the one that we're looking to find the corrections for. So let's just do an example. We have to, it's part of the problem. So this is the first state, this is the second order correction. So we have psi sub 2 h prime psi 1 all squared divided by E1 minus E2. And then we're summing this, so we have to do another one. And this will be our other wave function, so psi sub 3. And then we divide by our different energies. Yeah, just making sure I had the energies in the right order. And this is why we have a difference between degenerate and no degeneracy. Because if you have degeneracy, you have the same energy levels, well, you're going to be dividing by 0. So that's why, ultimately, we're going to want to have a new theory for that. Okay, so let's start with the first one. We have V naught 0, 1, 0, that vector, times minus epsilon 0, 0, 0, 0, epsilon 0, epsilon 0. So times this matrix and this vector. And hopefully you'll have 0 everywhere but that top part, which when you multiply it by the other matrix sheet, that'll be 0. So that is just one of the terms. We have 2. Well, we'll just do this. This part is 0. We'll do it part by part. That might be easier. So this is and now we're going to do the same thing but with this other eigenstate. So this will be 0, 0, 1. There's a V naught out here. Minus epsilon 0, 0, 0, 0, epsilon 0, epsilon 0, 1, 0, 0. Okay? And again, we can multiply this out. This will also be 0. So evidently, our second order correction, well, there is none. It's 0. And now we can do the same thing for psi 2. So E2, because that's this wave function, second order correction is essentially the same thing, only the order is a little reversed. And then plus, it's not too bad when you only have 3 states. You can kind of just write it out and it's not a huge deal. Though you can imagine if you had many eigenstates, this wouldn't be very fun. This would get tiresome. In fact, it can be generalized. What is this, third one? Where you can do more, but we'll do that a different day. Okay, so let's start with this first term. You have V naught 1, 0, 0. Then you have our Hamiltonian. And I'm kind of being a little slow with this. Like if you really wanted to, you could pretty quickly see which one of these is 0 and which one isn't. Let's see, that'll be 0, 0, so this one will be 0. That's this part. And then this part, we'll do it here. V naught 0, 0, 1. I don't want text mode on. I never use text mode, so I wish it wasn't an option. Zero, 1, 0. And this one actually will work out to be V naught epsilon. So that's cool. So then our energy correction, I think that's my dinner, is this squared, so V naught epsilon squared over the difference in energies between 1 and 3. So it's V naught minus 2 V naught, so minus epsilon squared V naught. And I'm going to eat dinner, and then I'll do the rest later. Okay, so now let's finish this problem. We are moving on to size 3, and we're looking for the second order correction energy. So E sub 3, second order. And this is going to work just like before. We're going to follow the same exact process. So just repeating this here equation. So this is a lot of little linear algebra stuff. If it's something you're not comfortable with, this problem should start getting you comfortable with it, which is what we're trying to do here. Okay, so now we need to calculate this stuff. So let's go ahead and do that. We have V naught, the Bra state. Then we have our Hamiltonian from the perturbation. And then our cat state. Okay. Alright, and let's see, this would just be V naught which is of course just 0. If we do it the other way, so V naught 0, 1, 0, our Hamiltonian, this time if you work this out you get epsilon V naught. So that one contributes, the other one doesn't. So our second order energy correction will be this squared divided by the difference between the unperturbed energies. So 2 V naught minus V naught, so just epsilon squared V naught. Now, of course, E1 equals E2 equals V naught means we have degeneracy. They're the same. So we really need to use degenerate perturbation theory. And whenever you have degeneracy, you're going to try to find your W matrix, where the elements of the matrix can be found with this equation. Okay. So for example, and for the record, we're only interested in our degenerate states. So what was it, psi 1 and psi 2? Yeah. So this is twofold degeneracy. The 1, 1 entry would be psi 1 and then psi 1. And now we just calculate this just like before, just calculating a matrix element. And let's see, this will be V naught epsilon. Okay. Now let's try W. Oops. One, two. And I believe this matrix is symmetric, so I want to say that's equal to W21. But we'll calculate them both just to be safe. I don't remember if that's actually a thing or not, so we'll just calculate it long ways first. That's something I'll have to look up after this video. But, I mean, it's fine. Worst case, you just get more stuttering now. Practice working on your matrix stuff. But this is a long video and I don't feel like redoing it, so I'm just going to look like an idiot, and that's okay by me. So that's 0. Let's see if that works with this other matrix. So that will again be second state. Let's see. Yep, that'll be 0. I don't know if that's always true, but at least in this case it is. So one more entry and then we're done. And that's going to be 0. Should have had a V naught with it, but whatever. It doesn't matter, it's still 0. Okay, so now we've constructed our W matrix, and that's going to be V naught minus epsilon 0, 0, 0. And you could, if you wanted to, solve the eigenvalue problem. The determinant of W minus lambda I, set it equal to 0. And just to show you, that would be the determinant of minus epsilon V naught minus lambda 0, 0 minus lambda, and that would just be, move that over, lambda epsilon V naught plus lambda equals 0. So you could solve for it that way, but it's already diagonalized, so it's not super necessary. And you get your eigenvalues of minus epsilon V naught, and of course 0 as an option. So then finally, our energies, E1 is going to be V naught plus lambda 1, so V naught minus epsilon V naught, or factoring out the V naught times 1 minus epsilon. And E2 is our energy, so V naught, they're degenerate, plus lambda 2, which we said was 0, so it's just V naught. And that is how you do this problem. It's a very long problem. It's more tedious than anything. You could do this a lot faster if you wanted to, but I wanted to show some of the steps. So hopefully that helps, and if it did, please like and subscribe. Thank you.